Okay, so in my last video we looked at simple molecular compounds, and here we're going to look at giant covalent structures. So here we're going to be looking at the structures that are these huge, massive lattices. This is still covalent bonding. So it's exactly the same kind of bonding that we had when we were looking at in our last video with those, like the chlorine molecules. But these don't form molecules of just a handful of atoms. These are ones that are these huge, gigantic, giant structures of atoms in just these, I'm talking like huge, 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 thousands upon thousands upon thousands upon thousands of atoms. So let's have a look at how these guys form. The covalent bond is exactly the same. So, giant covalent structures form in the same way as simple covalent molecules. It's all exactly the same. Let me just increase my line size a bit. It's all exactly the same. So say this time I've got a carbon atom. Here we go, carbon, 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 carbon. That is going to be, we're going to have a carbon atom here. We'll have a carbon atom here. Etc., etc. So this will go on ad infinitum. That'll be one here. So we're just talking about loads of carbon atoms kind of like linking up. And then this will sort of like extend that in this direction, and this, go off in all directions like this. So this will kind of happen ad infinitum. So in a giant structure, we have lots of alternating covalent bonds. All joined up together to effectively make one giant molecule. So all of these covalent bonds, all these atoms are joined together with covalent bonds, and there's hundreds and hundreds and hundreds and hundreds and hundreds and hundreds and hundreds of them. So you can imagine in something like this, in my carbon, kind of forms a little bit of a structure like this. This one will kind of come out. Now, those of you that have done your home learning will probably know exactly what this molecule is that I am drawing. If you don't know what molecule this is, I really do suggest that you do your home learning. It's really good to do that. You need to know exactly what it is that you are kind of talking about. Right, here we go, and then this guy will be down here. So this here, if I'm sure most of you have understood what it is, but this is diamond. And diamond is a really good example of a molecule. Sorry, not a molecule. A giant covalent lattice that is a really good example of kind of what we would expect giant covalent structures to be like. Okay. So this is how they're kind of stuck together. There's no intermolecular forces here. The only thing that's holding the atoms together are those really, 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 really strong covalent bonds. No intermolecular forces. This is not a molecule, not a molecule. I know I said it makes one giant molecule here, but obviously remember, if it's just one huge molecule, we don't call that a molecule anymore. We call it a lattice. Not a molecule, so no intermolecular forces. So in these giant structures, there are no intermolecular forces. So please, 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 do not write intermolecular forces in your questions about giant covalent structures, because a giant covalent lattice is not a molecule, so you do not have intermolecular forces. Right. So let's kind of have a look at the properties that these kind of have. First of all, the only thing that's holding these atoms together are those strong covalent bonds. So these are incredibly strong. So how do I put this? Giant covalent structures are very strong because the strong covalent bond is very difficult to break. Now, actually, diamond, as you may probably know, especially if you've done the home learning, covalent diamond is one of the strongest materials known to mankind. Incredibly, incredibly strong. So the only thing that can really cut another a diamond is another diamond. So like if you have a metal knife, you won't be able to cut diamond with it because the diamond is stronger than the metal. All right, let's move on. Let's talk about its melting point and its boiling point. You can see here that all of these bonds are really, really strong. So to overcome that strength of that bond, you need a huge amount of energy to be able to break those bonds. So a huge amount of energy is needed to break the bonds in giant covalent structures. So what does this mean? Therefore, they have a high melting and boiling point. Right, finally, final thing we're going to talk about is conducting electricity. Now, structures like diamond, these do not conduct electricity. Doesn't conduct electricity. Can you think why? We've come across this before. That's right. It's because there's no charged particles, and so if there's no charged particles, we can't get a movement of charge. So because there are no charged particles. So this is great for diamond and most other covalent substances, giant covalent substances. However, there are a couple of exceptions that are on the GCSE syllabus. You will need to know about the chemical graphite and graphene. These are two forms or allotropes of carbon that can conduct electricity. They're the only ones that can. What have I done here? I've kind of made a pig's ear of this drawing. Okay, cool. 1, 2, 3, 4, 5. Yeah, okay, that's fine. This is the worst drawing of graphite I've ever done. Right. If there's just one sheet here, like this, this is graphene. is a single sheet of hexagonal carbon atoms. Okay, and graphite, hopefully I'm a little bit better at drawing it here. Graphite's a little bit more interesting. So obviously we'll take a little bit longer to draw. There we go, much better. Okay, and then we'll have a second layer here. So the idea here for graphite is it's pretty much exactly the same structure as graphene, only there's loads of layers of it. So we have all these layers instead. They've got another layer down here. Sorry, this is taking so long to draw. You know, a cleverer person would have just done a little image instead of drawing these pictures out by hand. But you know, it's good practice. Okay, so in these structures, sorry, I should probably label this. This is graphite. You've got more than one sheet. In these structures, in this area here, so kind of like in between, so in this sort of like in-betweeny area here and here, these are areas of delocalized electrons. This means that the electrons are completely free to move wherever they want within that area. So, and if you remember, our idea of what electricity is based on movement of charged particles. Electrons are negatively charged, and because they're delocalized, these electrons, they're free to move. So that means that we can conduct electricity only in these areas. Now for graphene, the electrons can do that because they're there's this area of delocalized electrons kind of all over its surface like this. So it has an area of delocalized electrons as well. So in these areas of delocalized electrons, we can get electricity to pass through them. So for the vast majority of covalent compounds, they do not conduct electricity. But if you have a question about graphite or graphene, then you need to say that graphite or graphene can conduct electricity because it has an area of delocalized electrons. Therefore, it can carry a charge. Remember, that's because the electron is negative, electrons are negative, and in the delocalized area, that means it's free to move. So we've got a movement of electrons. Movement of electrons is electricity. That's what electricity is. All right, one more to go. Bear with me, it's not that long. You might want to take a break, maybe go to the toilet or something, and come back ready, refreshed, and we'll get on to metallic bonding.